If I don't start the recording now, I'll forget.
That's true.
We can edit that out later.
Talking, yes.
We can edit this out later, maybe, or not.
That's fine. It's part of the talk.
All right, for those who are showing up, we'll start in just a minute. People are still beaming in here, so we'll give folks a chance to assemble. All right, so you ready to begin, MingMing?
Okay.
Great. So welcome everybody to our summer seminar series of the CC Colloquium Series. I'm pleased today to introduce our speaker, Professor MingMing Li. Just a very brief introduction, since most of you know MingMing. He's been a faculty member in the School of Earth and Space Exploration since 2017, and he got his PhD here in 2015, just a couple of years before. And so many of us have known MingMing for a long time, and we're very thrilled that he was willing to come back and take on a role as faculty here with us. He came here after getting master's and bachelor's degrees in China at the Chinese Academy of Sciences in 2010, his master's in seismology, and before that a bachelor's degree in geophysics at Yunnan University in 2007. He's been here doing all sorts of pioneering work on computational geodynamics. We're going to see, I think, some fun fruits of that. I got to know MingMing in particular when he was still a student here, when he became involved with a research project that I was leading, a largely multidisciplinary research project involving research around the rise of oxygen in Earth's history during the first half of Earth's history. And we were exploring in particular the possibility that the mantle and changes in the mantle played a role in that rise of oxygen. And MingMing was very excited to throw himself into that and think through the geodynamic implications and consequences. And so it's been a real pleasure watching his career evolve, and a pleasure to have him come back here as faculty. So with that, I will turn it over to MingMing. And just one other note, if anybody's wondering if we have any announcements from CC leadership, we don't. I asked Ramon, he says there's no particular announcements, still waiting for the next round of guidance about return to campus issues. We're just gonna go straight into the colloquium here. I should have said that at the outset. So MingMing, take it away.
Thank you, Ariel. Good afternoon, everyone, and it's my great pleasure to share some of my research to you. I hope you will enjoy it and find it also interesting. And also, a lot of thanks to you to coming here during this special time. Please stay healthy and safe. So, today I'm going to talk about the multi-scale mantle structure and the convection. So one of my research focus have been focused on the structure and the dynamics of Earth's mantle. So this is important because almost all the geological events on Earth's surface, like for example, plate tectonics, earthquakes, volcanoes, topography, mountains, rivers, are all linked to the Earth's interior processes. But the question is, how are these linked, right? How do we understand the deep interior of the Earth, the deep structure, and also the deep interior processes of the deep Earth? This is a big question that, and is also one of my focus of my research. So I would say that one of the most important techniques that we use to see through the deep mantle, to see through the Earth's deep interior, is through seismic imaging. So the technique of seismic imaging is very similar to do medical CT scans. Like, well, can you imagine to do a CT scan for the whole planet, right? This sounds very difficult. actually it is all impossible. But what I want to say is that the technique is similar. Like to do a CT scan, you need energy, and the energy travels through the body, in the interior of the body, and you record the energy from different position, right? And then you analyze the signals, and which can, for experienced doctor, they can tell what that the signal means, and can make an image of the interior of one's body. And also similarly, for seismic imaging, we can use similar technique as CT scan, like, because for one thing, we need source, and the source comes from earthquakes. Like when earthquakes happen, it generates lots of energy, and the energy travels through the Earth's interior. And then on the other hand, we also have lots of seismic stations, and the seismic stations record this earthquake energy, and seismologists can look at the seismographs, and if they are experienced enough and have lots of practice and experience, they can tell what's happening in the Earth's deep interior. Like I remember when I was like small child, I learned how to choose watermelon by knocking it and hear the sound, right? And by doing this, I can tell whether a watermelon is sweet or not. This definitely not easy, and also need lots of experience. But the technique is also similar to seismic imaging, and both need lots of experience, right? And to the first order, although we are going to talk about heterogeneities in the Earth's deep interior, but to the first order, we need to remember that the Earth is layered, and 99% of the Earth is layered. Like the pressure and the temperature just increases with depth as function of depth, right? And this slide shows the density and the seismic velocity changes as function of depth. And here the horizontal axis is depth. And in the vertical axis, the green line, the green curve shows the density, and the red curve shows the P wave velocity, and the black curve shows S wave velocity. So the P wave and the S wave velocity are both seismic velocities, and the seismic velocity measures how fast seismic energy travels through Earth's interior. So as we can see, the density and also the seismic velocity, like to the first order, they all increases as function of depth, right? And the only exception is at least the common boundary from the mantle to the outer core. There is a significant reduction of seismic velocities, both P wave and also the S wave. Basically, the S wave becomes zero, because this is because our core is liquid. So, however, if we think the Earth is just simply layered, it seems a little bit boring, right? And also, indeed, if the Earth is indeed layered, that also means the Earth's interior is no longer active. Then we will no longer have like earthquakes, volcanoes. This can be a good thing, or actually it is actually a very bad thing for us. And luckily, there are some small perturbations of physical properties in the mantle. Like in this slide, I show some figures of seismic tomography results, from the 100 kilometers beneath the surface to the very close to the common boundary. And the last two panels show the vertical cross section, and the one is across the South Africa, and the other one is across the Western Pacific. I'm not out, and now what I want to point out is that we lost both large and small velocities in the Earth's deep interior. And also, I want to point out that in seismic images, there is a convention here. Like usually, people use red colors means negative seismic anomaly, and people use blue colors to represent fast or positive seismic velocity anomaly. And one of the focus of my research is to understand what causes these seismic heterogeneities, and also how do they evolve with time. And I use the technique of, geodynamic modeling. So the idea of geodynamic modeling is pretty simple. And we think that the deep mantle process, the physical processes are controlled by fundamental physical laws. There are not many equations we are dealing with. Actually, there are only 3 most basic equations, which can consist of like conservation of mass, which means the mass is conserved. It doesn't create or disappear by itself. The mass can only advect from one location to another location. And the second one is conservation of momentum. This is basically force balance, like F equals ma. And the other one is conservation of energy, like energy is conserved, like heat, but particularly the heat energy, right? And these 3 equations links a lot of physical properties together. Like this U is velocity, like mantle flow velocity. P represents pressure. This eta is viscosity. This C is strain rate, and Ra is a real number. T is temperature, and the BC are something related to convection, and this T is temperature. So we can see there are several important physical parameters here, and each of these parameters is a function of both space and time. So you can imagine if you want to solve these 3 equations by hand or using pencil and a piece of paper, it's very, very difficult or almost impossible unless you make lots of simplifications to these equations. And luckily, we now have computers, and we can solve these computers pretty easily. And we can solve these equations pretty easily using our computers. And particularly right now, we have lots of computer clusters, supercomputers. And by supercomputers, I mean tens or hundreds or even thousands of CPUs working together to do the parallel computing. And nowadays, the speed of computers becomes very, very fast and also becomes much cheaper. I remember that when, like about 7 years ago, when I published my first paper in geodynamic modeling, it took me about several months to do one calculation. But right now, the computer becomes so fast that I can finish the same calculation within several days. You can imagine how fast the speed of computers become right now. Like in this slide, in the figure at the bottom, I show myself and standing side by a cluster, which is here. And this cluster is now in the ISTB4 building on the 5th floor, and is our geophysics group. And also, our group also uses the ASU agave cluster a lot. The ASU agave cluster is pretty new and is very, very good. It's super fast. And also there are lots of CPUs, or almost 20,000. And also if you have experience with GPUs, they also have lots of GPU that you can use. And most importantly, I think ASU students and the faculties can create an account on ASU Agave cluster for free, and all people can use it. And this is the most important thing. And we have been taking usage of this for like since I came to ASU, since I returned to ASU at 2017. Like with these supercomputers, my daily work is to write codes and analyze my data, and also make images and videos. And I do this to test different ideas. And my goal is to also understand the fundamental physics process. Like depending on the scientific questions that you want to answer, models can be really different. And this can be have like models can have very different parameters, and also models can have very different geometry. Like here, I show some examples of the models I performed before. Like this one is the 1x1 box 2D Cartesian model. This one is like longer box, and this one is two-dimensional spherical geometry, and this one is 3D, partial 3D spherical, and this one is most complicated, and this one is like a full 3D global mantle convection models. And I'm going to show some of these convection movies later, so right now you don't need to understand anything. As I said, the models are set up for the goal of answering specific scientific questions. Like my philosophy is that if you can answer the scientific questions that you posed, the model should be as simple as possible, right? But the sad news, unfortunately, that I also most often I need to make the models more and more complex to make the reviewers happy. And before I jump into my details of my research, I want to introduce the two most important players of mantle convection, which is the subducted slabs and the mantle plumes. This slide shows a cartoon, like the subducted slab begins at subduction zones, and when the oceanic plates sink to the deep interior, the subducted slabs are usually several hundred degrees cooler than the surrounding mantle, and it sinks from the surface, and sometimes to the lowermost mantle, like which the Earth's core. And a mantle plume is different, and the mantle plume is relatively hotter, sometimes up to several hundred degrees hotter than the background mantle. And because it is hotter, then it's also less dense, and it usually rises from thermal boundary layer, like usually from the core mantle boundary or the bottom of the mantle to the surface. And we think that mantle plumes, when it reaches beneath the surface, it causes volcanoes such as the hot spots and the large igneous provinces. Like one of the most popular volcano caused by mantle plume is the Hawaii volcano. We are all familiar with it. And this is the model that I performed before in 2D spherical coordinates geometry. Like in this movie, the blue colors represent cold, cold subducting slabs, and the red colors simulates the hot mantle plumes. So, and I'm going to show similar convections of these kind of models later to you. And one of my focus of my study is to understand the dynamics of subducted slabs and the mantle plumes, and also these interactions with each other. So next, I want to show some examples of my past and current research, which is understanding the multi-scale structure and the dynamics of Earth's mantle. Particularly, I want to focus on Earth's lowermost mantle because it may be the most interesting and also most complex part of the mantle. So this slide shows an imaging of the global seismic tomography model, and from the surface to the common boundary or the bottom of the mantle. Like again, as I said before, there is a convention in seismic figures. Like people use red colors to represent a lower than average seismic velocity or with negative seismic anomaly, and the people use the blue colors to represent positive seismic anomaly. The first thing you may notice that in this figure is these two large low shear velocity provinces shown by these red patches. This is very big, and we call them LSVPs. The LSVPs are maybe the largest structure in Earth's lowermost mantle, and they cover about 30% of the common boundary area. And also surrounding the LSVPs are regions with showing by these blue colors, which represent higher than average seismic velocity. And these blue regions are often interpreted as the subducted slabs there. This is because people think subducted slabs are usually cold. And this slide shows a more beautiful view of the LSVPs, like it's in 3 dimensions. Now you can see these two LSVPs, one beneath the Africa and the other one beneath Central America. The LSVPs rises from the common boundary to about 1,000 kilometers above the common boundary, and these are very big structures. And also, another very interesting finding from observation is that the LSVP in the deep lowermost mantle has some connection with surface features. Like in this figure, the background color shows the seismic tomography model near the common boundary. Again, we see two LSVPs here, one beneath Africa and the other beneath Pacific. And these green circles show the locations of the initial eruption site of large igneous province. So the large igneous province are regions with extremely large amounts of volcanic rocks. And also this yellow color shows the active hotspots, and which maybe have a deep mantle plume origin. So we think that both large igneous provinces and the mantle plumes may be caused by or active hotspots may be caused by mantle plumes. So if so, then the question is why mantle plumes preferentially occurs at the edges of the LSVPs, right? Now, yeah, you can see most of these green and yellow spots occur at edges of the LSVPs. This is very interesting, and I'm going to show you that it is related to the large-scale mantle convection. And also, in addition to the very large LSVPs, seismologists also detect much smaller areas, structures, which are called ultra-low velocity zones, or ULVZs in short. In this figure, the pink color shows the location of the two LSVPs, and the red color shows the patches of ULVZs. You can see there's almost random. The distribution of ULVZs are almost random. And we can see both ULVZs outside LSVPs and also inside LSVPs. And there are also many ULVZs occurs at the edges of the LSVPs, right? So the LSVP has a seismic velocity reduction of a few percent, but the seismic velocity reduction of ULVZs can be like usually more than 10%, which is very big. And in addition to the LSVPs and ULVZs, people also found lots of small scale seismic anomalies outside LSVPs, but these velocities are not as low as ULVZs. Like in this figure, again, I show two LSVPs here, and outside the LSVPs you can see lots of red patches here, and these are also called seismic heterogeneities or low velocity structures outside the LSVPs. So to give a very brief summary, so like from observational point of view, we observed both large like LSVPs and small like ULVZ structures observed in the Earth's lowermost mantle. And also there are seismic heterogeneities outside the LSVPs, and also mantle plumes preferentially occur above the LSVP edges. So then the question is that what causes LSVPs, ULVZs, and other seismic heterogeneities, and also how these multi-scale structures are related to mantle convection. So let me first ask this question. So the first question is what causes low seismic velocity? So there are three choices. A is high temperature, B is different composition, and C is all of the above, right? And the right answer is I think you perhaps know the right answer is C. Like when you do a multiple choice question, like if you have no idea of the answer, you just pick something similar like this, like all of the above or none of the above is always correct, right? And so the next question is, what causes low seismic velocity outside the LSVPs? Like, I mean, these structures, red patches outside the LSVPs. This is a very interesting question. And the previous idea is that they must be caused by different conditions. This is in the subduction slabs, and that the subduction are cold and should have high seismic velocities. And that means they cannot explain the low velocity structures in this region. And as a result, this region must have different conditions. However, what I'm going to show you is that my recent finding is that actually these anomalies can be indeed caused by high increase of temperature, because I found that hot anomalies can form in subduction in influence region in the lowermost mantle outside LSVPs. So let me tell you some details of my model. So like these are some important features of these models, like 3D spherical mantle convection model, and the viscosity depending on temperature, depth, and mineral phases. And also I use Earth-like vigor of mantle convection. And also multiple compositional components are included. So this figure shows the geometry of the model. It's a 3D partial spherical geometry, and the boundaries are marked by these black curves, right? And here the green color represents a compositionally different and also compositionally dense material than the surrounding mantle. So let's run the movie quickly. So this is initial condition. Let's continue run it. So let me pause it here to point out some interesting features to you. So I show you in this figure, these cyan colors represent or they simulate the subducting slabs, and the green color represents compositionally distinct materials. And these gray contours or gray color represents the hot upwelling mantle plumes. Now you can see that the green materials are being pushed aside by the subducted slabs, right? And also another important finding is that mantle plumes forms preferentially at the edges of the green materials. And from now on, I'm going to call these green materials as thermochemical piles because they just piles up. Let's continue around this video, which can, and I'm going to point out more interesting features to you. So, and after some time, the subducted slabs is going to migrate from north-south boundary to the west boundary. And again, mantle plumes, most mantle plumes forms at the edges of this pile, the green pile. Now the subducted slab migrate to the west boundary, and also the green pile is being pushed to the east. So this is another very interesting finding. Like outside of the green piles, in this region is generally pretty cold. And however, in these relatively cold regions, you see lots of this linear structure, relatively hot, like red color means hot, and relatively hot anomalies here. And this slide shows some snapshots of the movie I just showed you before, like from figure A to figure B and to figure C. the subducting slabs migrate to the west boundary and the green thermochemical pile are pushed to the east. And the mantle plumes forms, most of them forms above the edges of the thermochemical pile. And also very importantly, like outside of the thermochemical pile, we find lots of linearized hot thermal anomalies and outside of the green piles. So like in this figure D, I show a 3D morphology of the hot linear anomalies. Like they have a ridge-like structures, and therefore we usually call them as thermal ridges, just for simplicity. So, and you may ask, well, how does this model related to the Earth, right? And from my understanding, like these green piles can represent the seismically observed very large scale LSVPs, and the mantle plumes here showing the forms at the edges of thermochemical piles or the LSVPs, and outside LSVPs, you can see lots of hot anomalies, and they have kind of linear structures. But what I'm going to tell you is that not all models can produce these hot anomalies. And I have been to a wide range of parameter space exploration. And what I found is that to form thermal ridges outside in thermochemical piles, you need to have relatively high core mantle boundary heat flux and also pretty vigorous low most mantle convection. And most importantly, the subducted slabs should have some thermokilogenities in it. And the next question is, what causes these thermal ridges, right? To answer this question, we need to zoom in to look into some details. Like as shown here in this figure is a zoom in temperature field near the core mantle boundary. So this is longitude and this is latitude. And the temperature, red means hot and the blue means cold. And in figure B and the figure C, I show the vertical cross section of the temperature field and the mantle flow velocity at two locations, at least B and in these regions are marked by C, right? And let's look at this figure B first. In regions marked by this B region, the thermal ridges have not fully developed yet. So now if you look at these black curves, you can see they all of them goes upward, right? However, in region C, when the thermal ridges are fully developed, you can see that in the lowermost mantle, the convection becomes much more complex. And this is because the small scale convections begin to develop during the development of thermal ridges. So that means there are at least two different scales of convection. To the first order, the materials are moving from west to east, right? This is the largest scale. And also there are lots of small scale convections imposed upon this large scale convection. And this is these small scale convections that are responsible for the small scale thermokilogenities. Now let's examine the seismic observations of UVZs here. As we already showed these figures before. Like the UVZs outside the LSVPs, I think maybe the thermal ridges can explain some of them, but the question is, how do we explain the distribution of UVZs inside and also at the edges of the SVPs, right? And also it's also a multiple choice question, and the high temperature, different composition, and also number C is all of the above, and the right answer is all of the above. And with both high temperature and also different composition can causes UVZs. And what I found is that UVZ caused by high temperature can have very different distribution than UVZs caused by different composition. Now, here is another model that I performed, and the geometry is similar, is the same to the model I just showed you before. And in this model, I simulate the UVZ materials as different composition. Like in this figure, the orange color shows the locations of UVZ material and the green color shows the thermochemical piles. The thermochemical piles are made partially transparent to allow us to see the orange UVZ materials. Right? This is only the initial condition, and let's run the movie. Now you can see very shortly after calculation, most of the UVZ materials are pushed to the edges of the thermochemical piles, right? And they have different size, different size, big and small, and also round shape and also linear shape of UVZs. And these features of UVZs are consistent with some of the seismic observations. However, if you compare the temperature field of this model, like I'm showing here, red color means hot and blue color means cold. Like the black curves here outlines edges of the thermochemical piles. And particularly, I outlines the hottest 10% regions in this model, which is shown by these orange contours. Now you can see that all of these regions occurs at quite some distance from the edges of the thermochemical piles, right? So that means if the UVZ caused by high temperature should occur further away from the edges of the thermochemical piles. So in summary, I found two types of UVZs, and one is chemical UVZ. The chemical UVZ preferentially occur at edges of thermochemical piles. And also the other is for UVZ caused by temperature only, and they should occur mostly further away from the edges of thermochemical pipe, like inside the SVPs. So finally, I would like to give a summary of my talk. Like seismic observations found these two large low shear velocity provinces in the lowermost mantle. These are very big structures, and also outside these large low shear velocity province, there are also some small seismic anomalies, right? And here, people also found that mantle plumes preferentially occur above the edges of the large low shear velocity provinces. And also people found much small structures of ultra low velocity provinces or UVZs. And the UVZs are found outside, inside, and also at the edges of the LSVPs. And my goal is to understand all of these observations, and I performed geodynamic modeling. And what I found that is the large scale LSVPs can be pushed by mantle convection to these current regions, like by subductive slabs, and also due to large scale mantle convection. And also there are small scale convection outside the LSVPs, and this small scale convection can cause like thermal ridges or thermal anomalies in the subductive regions. And these thermal anomalies may explain the small scale structures of UVZs and the seismic anomalies outside LSVPs. And also by doing a numerical modeling, I found that the chemical UVZs preferentially occur at the edges of LSVPs, and the thermal UVZs preferentially occur at the interior of the LSVPs, right? And the important idea is that so there are multiple scale structure and convection of the lowermost mantle. For the features of the large scale structure and the convection includes like the LSVPs are pushed by subductive slabs to these current regions, one beneath the Pacific and one beneath Africa, and also mantle plumes are advected by convection to the LSVP edges. And for the small scale structure and convection, the finding is that the small scale convection outside LSVPs, they can cause hot thermal anomalies in relatively cold regions. And also the small scale internal convection of the LSVPs can cause different distribution of thermal and chemical UVZs. So, and lastly, I also want to talk about something. Talk something about geophysics in CC. Like my research of geodynamic modeling is only part of the geophysics group, maybe very small part of the geophysics happening in CC. Like in geophysics, we merge imaging and modeling, simulate and predict the inaccessible interior structure and the processes. Like traditionally, the goal of the object of geophysics has many focus on the Earth, but nowadays, and we start to move from the Earth and apply what our techniques and our tools to understand the structure and the dynamics and the evolution of other solar and also extrasolar planets. And there are lots of techniques that we use, both like theoretical, numerical, laboratory, and observational. And like one person cannot do all of this, and we definitely need lots of collaborations in this. And luckily, we have all of this discipline. We have people working on different part of this, and we almost have a complete research disciplines in geophysics in CC. This is really great. And our goal is here to working as a team to better understand the structure, dynamics, and evolution of the Earth, like showing at this cartoon as the ants, like the ants come marching one by one, like the song. And another particular feature of geophysics in CC, like, is that the geophysics in CC is more like connecting tissues, like it connects lots of disciplines together, like volcanology, geochemistry, paleomagnetics, and like physics, petrology, and tectonics. And this is very, very great in CC. And finally, if you want to know some more of my research, and you can talk to me or you can come to my class. And I regularly teach coding classes like Python and geophysics and also geodynamic classes regularly. So if you want to learn more, please come to me or come to my class. So, and this is end of my talk, and please ask me questions. Thank you for listening.
Thank you. That was fun. So if folks have questions, you can put them in the chat, or you can put them in the Q&A, or you can raise your hand, and I'm happy to turn on your mic. And we can proceed from there. You're getting chat applause. And Steve Ruff has his hand up. Let me allow Steve to talk. Steve.
Yeah, hi, MingMing.
Hello.
I didn't understand literally the shape of your model in the lower left corner of this figure with the flat top and bottom. Yeah,
this
so
one.
I'm trying to understand, and that's how you had the slabs coming in from just the top and the bottom. So explain to me what I'm looking at in terms of the geometry of this shape.
Oh, it's let me see if I have other figures, and I actually, let me see.
I just was sort of confused at.
Hold on, let me do it very quickly. And the geometry is like this. I show you. Can you see my slides?
Yeah.
It's like shown here. It's a partial 3D domain. Like, it's not full global, but the depth ranges from the surface to the common boundary, and there are side boundaries. Like, it's only part of the global sphere, part of the sphere. So like, does that make sense to you? And right now we are looking from the top to the bottom. like this is top, and the surface of the top is larger than the common boundary surface, right? Because it's spherical.
Okay, I think I understand that. So then the green color material here is so the sort of bluish stuff is the slabs coming down, right?
Yes.
And then
yes.
and the green is the mantle somehow moving away.
Yes, the mantle material moving away because the pushing of the subductive slabs. That's why I say the LSVPs may be pushed aside to these current locations by subductive slabs.
Okay. All right. Yeah,
Okay.
that's good. Thanks.
Thanks for your question.
All right, there's another question. Somebody anonymous writes, what is the composition of the green material that is being pushed to the east in your model?
That's a good point. And they are right now these green materials, they are dense, intrinsically dense, compositionally dense than the background mantle. But for the composition, in our literature, there have been lots of debate for why they should be intrinsically dense material. And some people think they are caused by subducted oceanic crust, and another possibility is the primordial material that's being left over there after differentiation of the Earth. And currently, and Chen and I, and also Steve Dash and also BK are working on another hypothesis. And we think the green materials comes from the giant impact and the CR, which impact the proto-Earth, and they left there. And we're still doing some experiments to test this hypothesis. But to answer your question quickly, and the answer is we still don't know what's the composition, but there are lots of possibilities there. Thank you.
Thank you. Are there other questions? Oh, Kevin Trin is asking has his hand up.
Okay.
Kevin, you're on.
Okay, so I think I had a very similar question to what was just asked regarding the lower left figure.
Yes.
All the subduction slabs are on the west side.
Yes.
Wouldn't that imply that we'd see a lot of like tectonic plate boundaries on one hemisphere of the planet and none on the other?
So are you asking how this model compared to the plate tectonics, because plate tectonics have the other side, right?
Right.
Yeah, this is definitely very important question. Like the boundary of this side boundary is reflective side boundary, so like it's mirror side boundary, and also most often we cannot make a very direct comparison between models and what we observe for the true Earth. And our goal is the models are very, very simplified, and we use these structures to represent the subductive slabs, because there are some the most important feature, like for the Earth, the subductive slabs sink to the deep mantle. And to simulate that, I also have this cold material sink to the deep mantle. But I must say, it's very difficult to make a direct comparison with the true Earth. But that is very important question, right? This is due to the simplifications of models, and the question is, do we need to make the model more complex and also more real, more comparable to the Earth, and also make it more complex? So as I said before, my philosophy is just to make the model as simple as possible, as long as we can answer the question. So my question here is to understand what causes the hot anomalies outside in the subducting regions. I'm not sure whether I answer your question or not, but yeah.
It's I guess I'm more confused about why all of the blue is on the left and all of the green is on the right.
So the locations of these structures are mainly controlled by the model parameters, particularly the viscosity. And the reason is because every model is different. Like sometimes they go to the left, or sometimes they go to the right. And as I can show you, like in some other models, they are in the north and the east, right? So it's kind of related to the model parameters, and it's very difficult to predict. And I don't know how to answer this question, but this is definitely related to the model parameters that we choose.
Okay, I think I see what you're getting at.
Okay. Sorry for confusion.
So we have another couple of questions. Thank you, Kevin. So Maitri Bose asks, she says it's a naive question. What are the velocities at which material moves up or down? What are the timescales with which these structures form?
That's a really good question. And let me show you this movie again. The time scale is showing on this top. It's like basically the time scale is on the time scale of hundreds of millions of years, right? It's pretty slow, and the velocity is different from place to place. Like in the up mantle, the velocity is similar to the velocity of plate tectonics, like several centimeters per year. And in the low mantle, because the viscosity is much large, so then the mantle flow moves relatively slower, like maybe 1 centimeters per year, approximately, but on the scale of centimeters per year. And these structures form on the time scale of hundreds of millions of years. And what's the other question? So Paras asked, what kind of programs or language do you use to do these simulations? Yes, I use the C program language, and the code is called sitcom, and this is open source code. So you can download free online. And if you want to know more, like in my geodynamics class, students all get lots of experience to perform the mantle convection models by themselves. So if you are interested in, please come to my class next time.
And we now know how to do well on your multiple choice questions too in your class. So you've told all the students how to do that.
Okay, so that's good point.
So with that, we have time for 1 or 2 more questions if somebody has one. Otherwise, let's thank MingMing for a great colloquium and a beautiful talk, beautiful visuals, and a lot of cool science. So thank you very much. Next week will be Christy Till, who will be giving a talk titled New Insights into Magnetic Systems. So another one not to be missed, especially if you're interested in Earth's interior and how it affects the surface. So look forward to seeing many of you next week. And thank you very much. And thank you, MingMing.
Thank you, everyone. Bye-bye.
Bye.